Hi again to this video. In this video, I would like to show you how much power and energy we actually have in such a solar spectrum. So we looked in a previous video at where the spectrum, this reference spectrum, comes from and how it is plotted. And now in this video, I will show you how to calculate the power in this spectrum. So this is the spectral irradiance that is given here. That is, we see plotted the power in watt per square meter of area on the surface and per nanometer of wavelength here in the spectrum. Also, the spectrum, as we saw previously, is given for the extraterrestrial spectrum, AM0, AMAS0, and for the AM 1.5 locations, that is, for example, in Europe. So if we now want to know how much power is in the spectrum, we need to integrate. So this is shown with this equation here. So we have, if we want to calculate the total power that is incident, that is the PINC, that is the incident power, then we need to integrate over the spectral irradiance. And the spectral irradiance I called here L sub lambda. The spectral irradiance is also called often E, but E we also call the energy, and in order to not confuse the energy with the irradiance, I call the irradiance here capital L. And L lambda is then the spectral irradiance, that is the irradiance per nanometer wavelength. So in order to determine the total power in the spectrum, we need to integrate the spectral irradiance over the wavelength lambda, and we need to multiply it with the surface A of our solar cell in order to know how much power is incident onto the solar cell. Down here, the units are also given. So the power is given in watt or joule per second, energy per time. And the spectral irradiance is given in watt per meter squared per nanometer often, if you look at the graphs. If you look at it in SI units, this would be the same as watt per meter cubed. Okay, so let's look at the MATLAB program in order to integrate this spectral irradiance here. Okay, so let's look at our MATLAB program. This is the MATLAB program we did in order to read in these reference spectra from the Excel file. I already showed you how to plot the spectral irradiance. And what we are going to look at now is the integration. So the integration part I added here at the very end. And in order to do the integration, I first of all want to integrate for all three different scenarios. So therefore, I first of all define variables L spectral 1, 2, and 3. These are the spectral irradiances. And I use first of all here the extraterrestrial spectrum. Then I use for the second one the global tilt spectrum. And for the third one, I use the direct spectrum that we have. And in order to do the integration, I initialize three variables. These will afterwards include the result. And then I do a for loop over all of the wavelengths lambda that I have. And for each wavelength, I calculate the value of the spectral irradiance plus the spectral irradiance at the next value, II plus 1. So II is my running variable here. And I multiply that with the spectral with a distance in nanometer between the two different wavelengths. So lambda II plus 1 minus lambda II. And this result, that is the spectral irradiance in this wavelength interval where I'm at the moment. And so this delta L1 I add to my L total 1, so that was initialized to 0, and then I added for all the different wavelengths integrals, and therefore I get the numerical approximation of the integration by doing this kind of triangular approximation. And this I do for all 3 spectra, and therefore at the end I have my total spectrum, and this total spectrum I can then output, and the output, I will just do the output here, so I remove this, okay, remove that, I run the total script, and I get here in the command window the results. So what I obtain is that for the extraterrestrial spectrum, we obtain a total irradiance by integrating the spectral irradiance of 1,348 watt. For the second value is then exactly 1 kilowatt, that is pretty much exactly 1 kilowatt, that is the global irradiance. And for the direct irradiance, we get 900 watts. So now we know what the content is in the spectrum. And let's go back to the slides. Okay, so here we are back at the slides. I used now this integration, did it numerically in MATLAB, and these are the values that we obtained. For AM0, that is the blue spectrum in the graph here, we get a total power of 1,350 watts per square meter. For the AM 1.5 global, we get 1,000 watt per square meter, and for AM 1.5 direct, we get 900 watt per square meter. So this is the incoming power per area, and of course to get the total power we need to multiply with the size of our solar cell or solar module. These spectra here are the reference spectra, as I told you. So now let's look a bit more in detail at how is it spatially distributed, the irradiance over different locations. And for this I will just show you on the web what we observe. Okay, so here I'm on the website Global Solar Atlas, and on this website you can actually find a lot of information on the irradiance as a function of location. And for example, you can see this nice map down here. So this map shows us all of the information for different locations on Earth, and this map actually shows it then the power multiplied by the time that we have that power, so it gives us the energy that is available. And it gives us the energy in terms of the daily totals, so that is this upper row here, and also we see the yearly totals, that is this lower row, and the unit is kilowatt hours per square meter. So the irradiance that we just had in watt per square meter needs to be multiplied by the duration that we have this irradiance in order to get the total energy that we can obtain at different locations. And here you can see from this graph that, of course, here in the Sahara, where there's nearly no clouds and close to the equator, we have the highest available energy. And this energy is actually around 7 kilowatt hours per meter squared in the Sahara. If we are now in Germany, so if we are up here at Kiel University and up in northern Germany, then up in northern Germany here we have a value of around 3 kilowatt hours per meter squared per day on average. And then the yearly average you can multiply, you can see here at the lower row if you multiply it by the days, and then you see that in Germany, in northern Germany, we get around 1,000 kilowatt hours per meter squared per year for our solar modules as irradiance. This is not talking yet about how much electrical energy we get out. It's just the solar irradiance that we have. Okay, so also on this web page, you can actually select different countries. So you can, for example, select Germany here and get a fact sheet also on what is happening as a function of the time in the year. So how much do you have per month, and what do you observe? What do you observe at the different locations within Germany? And also you can find what the deviation is. So let's look at one more website, and this here is the Deutscher Wetterdienst. That is a German website, and this website, the DWD, this actually shows us for Germany what the monthly sums of kilowatt hours per square meter are on average. And here's the average taken from 1991 to 2020. And also it gives for the current year 2024 what we have observed, what we have obtained so far as irradiance. And here you can see for Germany in winter we have a rather low, the sun is low on the horizon, and we have often cloudy weather, so we get only a little solar energy. But in summer we can then get much more solar energy because the sun is higher up, so the air mass is lower, and also we have less cloudy days, so therefore we get more irradiance in Germany during the summer months of May, June, July, August. Okay, and if we want to check what we get actually per day, we can check our own photovoltaic system that we have at Kiel University. So this is our web page here, and on our web page we can see down here the solar energy that we obtained. So this is given here as the power, so the kilowatts, so it's and the kilowatt hours are given in red. So the power is given in blue, and the energy, the kilowatt hours, is given in red. And you can see here that yesterday we had some sun coming in during the middle of the day. We got more solar power out, then we got solar power out of course during the night there's nothing at all, and also in the morning and in the evening we have less solar power than at midday. And this of course depends on the month. So let's check a different month. So let's, for example, take August here. Okay, if we check, for example, these 2 days in August here, then we see that on this day, which was the 16th of August, we had a lot of sun, and so we had a lot of power at our location here at Kiel University, while on the 17th of August, the weather was cloudy, and so because of the clouds, we have a lot less energy available than by solar radiation. What you can already see nicely from these graphs here is that we have quite a variability of the energy that is available from solar power as a course of the year, and also as a course of the day, as we can see. Okay, so let's go back to the slides. So in summary, we have a variation of the solar radiation with location on Earth. And this is typically expressed in terms of the global horizontal irradiation. That means you take a horizontal surface and measure what the irradiance is integrated over the year in order to get the kilowatt hours per square meter at certain locations. And as I just showed you, we of course also have daily variations and temporal variability. As an example here, the curves for Kiel University. Thanks for watching.